Okay, with that much said, I'd like to turn the presentation over to Philip Ling, who's pre-recorded his part of the presentation. Philip, go ahead.
Thanks, Mike. I appreciate being here, and I look forward to talking to you about transformers because, you know, the reality is these beasts are tucked away in a closet, you know, behind a locked door, and are really left and unattended for many years. On the good side, that means not a lot of maintenance is required, but you know, on the flip side, it means that you know, people aren't really conscious about, you know, what their impact is on an electrical system. So you know, in terms of these transformers inside the building, you know, these low voltage dry type transformers, we're talking about 40 million of them around the country. And so they're in every building, doesn't matter what vertical market, whether you're a hospital or a school, there are these type of transformers in every building. According to the DOE, over 50% of these transformers are 30 years older or more. And when you overlap that with the mean time to failure of a low voltage dry type transformer at 32 years, you can see that, you know, there's going to be quite a bubble of activity, should we say, related to transformer replacement over the years. The DOE noted in terms of losses, which you can see is very substantial, 60 to 80 billion kilowatt hours a year in transformer losses. So environmentally, you know, lots of coal burned just to feed the losses in those transformers, lots of grid tied up associated with that. And so in terms of carbon footprint, same thing, big impact on that front. A couple of things you really have to know. First of all, you know, we're living in a world where transformers are much more likely loaded than we think they are. You know, and that's, you know, a function over all these years. You've got code that's being very conservative in terms of calculation. There's the design engineer allocating for future load growth, and then you're overlaying on top of that an evolution of the loads that we're connecting to actually smaller and smaller power supplies. So you've got what used to be a desktop computer at a couple hundred watts, you know, 10, 15 years ago, we're down to laptops with 15 or 20 watts. A huge difference in consumption. And as a result of that, you know, in both the Cadmus group, who in 1999 produced the study of these transformers, which you can see in the top right, where 15 to 25% load is what's typical across all these vertical markets, offices, manufacturing, retail, and so on. Our own extensive field experience, which you can see in the bottom left, in terms of loading of transformers, 35% being the EPAC 2005 reference load upon which you know, efficiency requirements are required for transformers. You can see from that scatter plot that we're talking about much lower than that on average. And this has several implications. So as you can see here, what those implications are overlaid with a typical transformer efficiency curve is you can see, yeah, I've got the loading in blue stacked to the right-hand side, and in the 10, 15, 20% range. And then on top of that, you see that purple line being the efficiency of a typical transformer. And as you can see, it noses off really rapidly as you get down to lower and lower loading. So this means that there's kind of a disconnect between the nameplate efficiency and the target efficiency that is required by law, which is set at 35%, and the actual environment that the transformer is operating at, which being much lower load means much lower efficiency. So there's really an illusion of efficiency in transformer practice because of that light loading reality. The second thing you've got to consider is what are we connecting to transformers? We are connecting electronic equipment, and we're not connecting incandescent light bulbs anymore. And what that means is that the load profile is important. So we have a look at it, and you look at electronic equipment, single phase in this case, so stuff you plug in at 120 volts, draws pulses of current instead of current continuously. And as a function of that, the efficiency of the transformer is further decreased, right? So now you're talking about a transformer that, if we look at the blue line, that's the operating efficiency of a typical transformer under nonlinear load compared to the line above it under linear load. So you can see that there's a gap there and that quick drop off. So really, if you're going to provide a transformer that's suitable today for the application and you're going to deliver real-world savings, you've got to come up the efficiency curve very quickly at light load, and then you've also got to minimize that gap going from linear to nonlinear load, which you can see is achieved at the top transformer. And that's really what you're looking at in order to make things work today. So this is an example of, of typical savings scenario for a 75 kVA, which is, one of those average size transformers which you see in buildings. You've got before and after. What you got here, as you can see, 75 kVA. We go down to the loading line, which is, the next bullet there. We're around 13% loading on average. You look at the gap in losses. The before transformer, 936 watts. After, down to 235. So about 700 watts of savings. This is obviously equivalent to, the reality, 700-watt light bulbs left turned on for 30 years. So you're going, whoa, this closet has all those light bulbs that will never burn out. So you figure, you start to do the math on that, and even though you may think it's a handful of watts, you start to do that year after year after year, and over increasing energy rates, I mean, that's a pretty big number, and this is quantity one transformer. That, by the way, those losses will pay for the transformer roughly 20 times over its life. That's the difference between first cost and life cycle cost for a transformer. So to summarize the transformer story, we've got a much bigger electrical infrastructure than we need. So we're wasting capital by putting not just the transformer in, but the surrounding breakers, conduits, conductor sizes. We're at the bottom end of transformer efficiency because we put in such a large infrastructure. The reality is, of course, we're feeding electronic equipment, so that has an impact on the load profile, the efficiency of the transformer. And actually what it means is you got to be careful not to put in a general purpose transformer, because you end up with a UL issue as a function of not having a transformer appropriately listed for the load profile. So what you've got to do, obviously, right size wherever possible, very, very important. Understanding that there is this overcapacity that's built into the numbers that we're using. And the second is understanding that reality. Make sure the transformer is specified to maximize efficiency under those low load electronic equipment load profile conditions. So that's my piece. Mike, back to you.
Thank you, Phil. This is a mark between Phil's first take and his second take. And that's our part of the story for the moment. Phil, would you like to continue this for us?
Just a second. I got a call I got to take for 2 seconds.
So that's one part of the story. We wanted to drill down in a little more detail, and we're going to have the privilege of having Phil Ling from Powersmiths, our co-author, explain to you a little bit more about the transformer side of this. So, Phil, please carry on.
Thanks, Mike. Yeah, the transformer is a pretty interesting beast, actually. It's one of those things that behind closed doors, locked away in a closet somewhere. Once it's installed, no one really pays much attention to it, as you can see in this picture. There are about 40 million dry-type transformers installed across the country, and statistically, it's important that we understand about half of them are over 30 years old. With a mean time to failure of 32 years, you can see a pretty good conflict or a change-up that's going to be required over that time. The environmental impact is substantial. The energy impact is substantial for these transformers, because while they're small and one might think insignificant, when you add those numbers up, we're talking 60 to 80 billion kilowatt hours a year, 145 million tons of coal burns just to feed those wasted watts that are coming off as heat in the transformer. So carbon footprint contribution. So it's grid capacity and cost. So a pretty big deal for something that's really doesn't get much thought. So as we go to the next slide, what we see is that transformers are not as loaded as we think they are. And in fact, we're seeing that load across the top right-hand corner is a publication from the Cadmus Group, who did a survey of transformer loading in the northeast of the country. As you can see, loading ranges from 10 to 25% across all these vertical markets, so office, manufacturing, retail, schools, healthcare. So, you would expect that, at first blush that they would all be quite different, but that in fact is not the case. We've got out in the field ourselves. We do a lot of work in the field replacing transformers, and as you can see on the bottom left, our findings are really quite similar, as you can see from the scatter plot. And that's important because the legislation for minimum legal efficiency for a transformer references 35% load, and as you can see, we're far below that. And as you can see on the next slide, that that has a significant impact in terms of operating efficiency in real life compared to what you would think of a 35% load point. So here we have in blue, you have the loading profile of transformers, as you can see, stacked to the left, light load, that 35% reference point of the legal requirement, and then overlaid on top of that is typical transformer efficiency curve, which you can see peaks, in the 30, 40, 50% range, but drops off very sharply at lower loading, and that's a problem because realistically, that's where transformers are running. So there's if you're looking at the technical data sheet of a transformer and you go, oh, it should be this efficient. In fact, once you run it, it's substantially lower than that. So if we go to the next slide, you can see the other thing we have to keep in mind is the profile of the transformer. So what is that load profile? And you go, well, it's quite electronic in nature. Oh, Mike, we're going to have to stop for a second, restart.
Okay.
Because it skipped over one slide.
So that's this part of the story, a basic overview. I wanted to drill down a little bit more detail now, and we've got the pleasure and the privilege of having Phil Ling talk to us on a recording, and as co-author. No, I don't like what I'm saying. I'm going to stop that. Well, we now have the privilege of having Philip Ling, our co-author, speak to us from his offices at Powersmiths. So, Phil, please carry on.
Okay, hold it. We're going to have to scroll up on the left, and I can't. Can I do that? I don't think I can do that from. Can you scroll up the slide so I can see all of them?
Oh, yeah. Here's how you do that. Well, that's the introductory part of the story. We'd like to get a little bit more detail on the transformer part of it, so we have the privilege of having our co-author speak to us from a pre-recorded file. And Phil, I'm going to turn it over to you.
Thanks, Mike. All right, I'm happy to talk to you a little more about transformers. Transformers, as you can see on this next slide, you really don't get a whole lot of respect. They're in there tucked in a closet behind locked doors, and on the bright side, they don't need a lot of maintenance, and that's kind of why they get forgotten. But on the flip side, they're actually burning a substantial amount of losses, and as a function of that, it's costing us money that we're not thinking about exactly because they're tucked away in these closets. There are a whole lot of these low voltage dry type transformers. The DOE estimates around 40 million of them. The other thing that's important to us is that about 50% are over 30 years old, which is very close to their mean time to failure of 32 years. So you can see there's an upgrade cycle is going to come, and that's important because, as you can see in the next few slides, that we have an opportunity, really a once in a generation, to optimize the transformer for the application. In terms of energy and environmental impact, we're talking about pretty big, summed across the country, 60 to 80 billion kilowatt hours of losses. So there's dollars, obviously, and grid capacity tied up with those. About 145 million tons of coal need to be burned to feed just the transformer losses. So pollution and CO2 footprint consequences. So the transformer is not something to be ignored. As we can see on the next slide, the important thing that we first have to look at in terms of what the right kind of transformer is the load profile. So first of all, we're going to look at loading in general, and as you can see on the top right here, we've got the results of a CADMA study in the Northeast of transformer loading by vertical market. And as you can see, we're regardless of the vertical market, healthcare, schools, retail, manufacturing, office, they're all in the 10 to 25% loading range. So it's really not like that one is particularly different from the other. So that's one takeaway. The second takeaway is that, whoa, we're talking about 15, 20% loading. So we're talking about an electrical infrastructure that it's as much as 5 times oversized. So we're seeing the same. We're out in the field replacing transformers all the time. Bottom left, you can see all the scatter plot of loading of transformers. You can see we're down in that same kind of load range. And particularly what I've done is overlay the 35% loading level, because that's dry type transformers are regulated, so there's a minimum legal efficiency, and that is referenced at 35% loading, which, as you can see, is not exactly relevant to the population of transformers. And we'll see on the next slide why that's important. Well, it's important because transformer efficiency is a curve, and as you can see, it peaks in efficiency 30, 40, 50% load, but as you lighten up, you start going 30, 20, 10, the efficiency of the transformer noses off. It just falls off a cliff. And guess what? That's exactly where the loading is. So you have the impression at one hand, because there's this minimum legal efficiency, that you're going to get that efficiency. But in fact, because the loading's not there, you're not anywhere near that kind of efficiency, right? And losses are the flip side of efficiency. So you can see, 96% efficient transformer means 4% of losses. Down at 10% load, we're at a 90% efficient transformer, meaning 10% of losses. So we've gone from 4% to 10%. So pretty big difference in terms of where we think the transformer is operating. So loading, as you can see, very important. On the next slide, we're going to look a little more about what that load is made up of. And as you can see, we just think about low voltage, so 120 volt, all these receptacles. What are we plugging in? Well, we're not plugging in baseboard heaters and incandescent lights. We're plugging in electronics, right? And when you look at the load profile of a piece of electronics, this is a 120 volt, switch mode power supply, which is very common. As you can see, there's pulses of current instead of a nice sine wave. And as a function of that, introduces quite a lot of extra heat into a transformer. And as a function of that, reduces its effective capacity. And that's important from a couple of perspectives. First of all, if you have a general purpose transformer, or if you were thinking about specifying one, you've got a UL listing problem, because those transformers are designed per the UL spec to 5% THD being the limit of what its UL listing is for. As you can see by the scatter plot of current THD from a sample of transformers, you can see they're almost all of them above that, not just a little bit above that red line limit, but far above it. So what it means is a general purpose transformer, definitely not approved for that purpose. So from a new construction perspective, so retrofitting a transformer, it means you can't retrofit a general purpose transformer into that same space. You've got to recognize that the load profile is different, and as a function of that, put in a transformer that is K-rated for that kind of a load profile. So now we've got a light loaded transformer and the reality that we're feeding electronic equipment, right? So the next slide shows what the impact of that is from an efficiency perspective. So the bottom pair of curves are the linear load in purple, and the blue line nonlinear load. So as you can see, first of all, that the efficiency at low load is low, but you can see quite a large gap as that load profile has changed from a linear ideal sine wave load down to the nonlinear load reality which we're feeding in real life. So the right kind of transformer for the modern application is a transformer that, first of all, has a rating for that nonlinear load. The second thing is got to address the light loading reality, so it's got to peak at efficiency very, very quickly. So as you can see, that's where we're getting at the top here. The second thing you've got to look at is going, okay, well, I'm not feeding light bulbs, I'm feeding electronics, and I've got to minimize those incremental losses. I don't want this giant gap that I see with a typical transformer. I want to narrow that. So that's really a combination that you're really looking for. And what that means is shown on the next slide. I've taken a transformer before and after from a school location here, and it's 75 kVA transformer, very typical transformer size. As you can see, going to the second line there, we're talking about a 13% average load, so we're in that typical light loading range. you go down to the next line, 936 watts before, 235 watts afterwards, so a 700 watt reduction. So, very typical, first of all, of what you find, almost a kilowatt of losses for a 75, cutting it down to a couple hundred or so. So you say, there's your opportunity for savings. Now, just think about it if you, in sort of, translate it into sort of an equivalence we can understand. Here you've got this electrical closet where you've got 900 watt light bulbs turned on for 30 years, and you can cut that back down to 2. So effectively you're saving 700 watt light bulbs turned on for 30 years that'll never burn out. So the math ends up being really big because these transformers are installed for such a long period of time. So the next slide summarizes the takeaway for transformers. First of all, they're lightly loaded, so as a function of of code considerations of an electrical system designer, allowing for this load growth, but overlaid on top of that, the fact that the equipment that we're connecting is getting more and more efficient and therefore drawing less and less load, is that we really are in a situation where we've got infrastructure that's very commonly 4 or 5 times too big. That's a lot of wasted dollars, right? And from an operating perspective, you're operating right at the bottom range of the transformer. The second reality, we're feeding electronic equipment, so we've got to get a transformer that's UL listed for that application. We've got to recognize that there are increased losses for that profile that have to be minimized if you're going to run an efficient system. So to summarize the two, there's a big right-sizing opportunity as we go in to retrofit these transformers, or even from a new construction perspective, make sure you size a transformer absolutely as tight to the load as you can, because otherwise you're going to have this drastic oversizing. The second thing you want to do, make sure that that transformer is optimized for what we see, so light loading, electronic equipment load profile. So there's the transformer in a nutshell. Back to you, Mike.
Thanks very much, Phil.